All right, so welcome to the fourth and I think final video for chapter 2. We're going to cover sections 2.5, 2.6, and 2.7. So 2.5 covers an idea called an empirical. An empirical means based on data. So an empirical cumulative distribution function, an ECDF. So pause it, copy it down, and then press play again. All right, so the idea here is we're going to be given some data and we're going to create what's going to mimic a CDF for that data. Now, if I just give you data, we don't know what the distribution is. So we can't hope to get like an actual distribution CDF as a function. So we're going to make an empirical version of it. So we're going to have n data points, and we're going to denote our ECDF as f hat. And it's going to be defined very simply. If you give me an x value, I'm going to count how many of my data points are less than or equal to that x value. And then I'm going to divide by the total number of data points that I started with, okay? And as a result, we're going to see that the graph of f hat is usually a step function. So it's usually going to be horizontal, jump up, horizontal, jump up, horizontal. So it's sort of a step function, okay? So let's do an example to help get this idea clearly in your head. Here's the data set. I give you the values 3, 6, 15, 15, 17, 19, and 24. So I've given you 7 data points, okay? One of the data points, 15, is repeated twice, and we'll see the effect that has. All right, so let me just try and calculate f hat at some specific x values. So let's try f hat at 0. Now, the number of data points that are less than or equal to 0, if I look at my data set, I don't have any that are less than or equal to 0. So f hat of 0 would be 1/7 times 0, which is 0. And similarly, f hat of 2 and 2.9, none of the data points are less than 2 or 2.9, so I still have 0 for my f hat value, okay? But once I hit 3, I have 1 data point that's less than or equal to 3. So f hat of 3 would be 1/7 times 1, which is a 7. All right, well, f hat of 4, 5, 5.2, 5.9, f hat of all those values, there's only 1 data point, 3, that's less than or equal to 4, 5, 5.2, 5.9. So for 4, for 5.9, I still only have 1 data value out of 7 that's less than or equal to those guys. So my f hat value continues to be 1/7. All right, once I get to f hat of 6, though, I now have 2 data points that are less than or equal to 6. So f hat of 6 would be 1/7 times 2, or 2 sevens. And f hat of 7, 8, 9, 10, 11, 12, 13, 14, 14.8, 14.9 would all be 2 sevens, because there's exactly 2 data points less than or equal to 6, 7, 8, 9, 10, 11, 12, 13, 14, 14.2, 14.9, okay? Once I then hit 15, I get a big jump, because f hat of 15, there are 4 of these data points that are less than or equal to 15. So I jump up to 4/7. And I could continue to play this game, okay? So let's graph it and see what it looks like. Less than 3, there are no data points, so f hat is 0. Once I hit 3, though, I have f hat value of 1/7, and that stayed until I got to 6. Once I hit 6, I jumped up to 2 sevens, and f hat stayed the same until I hit 15, where it jumped up to 4 sevens. It jumps up again at 17 to 5 sevens, and then at 19 to 6 sevens, and then at 24, it jumps up to 7 sevens and stays there forever afterwards. So since there's 7 data points, I divide it by 7 because at 24 and beyond, all 7 of the data points are less than or equal to whatever x value you get. So you'd have 7 times 1/7, which is 1. And a CDF has to go from 0 to 1, right? 0 probability to 100% probability. Okay. All right, so, and look, it's a step function. All right, so let me do a quick little beer wings example. We're going to use this a couple of times. So I'm going to shift over to R. It's the same R file that we're using for everything here in chapter 2, at least. There it is. And share. Okay, so I'm looking at a data set called beer wings. And here. Put that out of the way. Okay, let's just look. Line 76 says view beer wings. So let's just look at what we're dealing with. So here's the data set, the top left. I imported a few things, an ID of the person, 1 through whatever we got, 30 maybe. Hot wings is the number of hot wings that person ate. Beer is the number of ounces of beer that person drank, and then genders if they were a female or a male. Okay. So I looked at 30 people sitting in, I don't know, Buffalo Wild Wings, and they counted how much beer did they drink, and how many hot wings did they eat, and do they appear to be a male or a female? Boom, there's my data set. All right, I'm going to close that. Well, I can just go back to that window. All right, now line 78 and 79, what I'm doing here is I'm just going to focus on the men. So I'm going to define a new data set to be beer, capital M, and it's a subset of the beer wings data set, and I'm going to select beer, and I'm going to select men. All right, so that's what beer M is going to be. It's just going to look at the men and how much beer they drank. Or I can do beer female, just look at the beer the females drank. So I run both of those, so R knows what I mean by beer M and beer F. And now I'm going to plot the ECDF for beer M. And it looks like I'm going to label the x-axis by ounces. So let's just run this command, which is line 83, I believe. All right, and there I get an ECDF for the beer the men drank. And then it looks like a step function, right? Similarly, I could run an ECDF for the women. And this is running it on the same exact plot, which you should see on your lower right. And so it looks like the women are lagging behind the men in how many ounces they tend to be drinking, the probability of drinking things. And then I think the next command I just throw in 25. I think that was the average amount of beer any of these people drank, like the whole group drank. And then this legend thing, I don't care about it, but I'm sure it does. It kind of plops over that. Okay. All right. So that's in your file. Now you know how to plot an ECDF for some data. All right. So let's go over to scatter plots, which will not take too long. Okay. So scatter plots. Again, pause, copy down that panel. All right, so a scatter plot. This is when I've got sort of two variables, and I sort of want to see, are they influencing each other? Is there a relationship between them? Like the beer wings example, is there a relationship between the amount of beer drank and the amount of wings eaten? Maybe, I don't know. So scatter plot is used for looking for a relationship between two variables in a data set. And all we're going to do is we're simply going to plot these points. So for each person, I could form a coordinate, the number of wings they ate, comma, the number amount or ounces of beer they drank. That's 1 point, plot it, plot them all, okay? So I'm simply going to plot the data points. By convention, the variable of primary interest is plotted on the vertical axis, and the variable that we think might help predict that primary interest variable is located on the horizontal axis. So I might think, well, the more beer wings they eat, the more beer they're, sorry, the more wings they eat will cause them to drink more beer. So I might think it's the wings being eaten that are driving beer consumption. So I might wish to plot it. So on the horizontal, I put the number of wings, and on the vertical, I put the ounces of beer drank. If I'm a bar owner, Buffalo Wild Wings, maybe I think to myself, well, if I lower the price of wings, they're going to eat more of them. And I'm going to get my money back and more because they're going to order more beer. And I can sort of jack the price up on the beer a little bit. Okay. All right. But who knows? All right. So let's go back to R and see what a scatter plot looks like with the beer and the wings. All right. So scrolling down to section 2.6. I've got 3 different commands on lines 91, 94, 87. But I think they're all going to do pretty much the same thing, but just one's a fancier version of the other, perhaps. All right, so let's just look at line 91. It's asking me to plot beer versus hot wings. So that's that first bit, beer, hot wings. Those are the names that your columns, so I have to get those names exactly right, or R won't know what I'm talking about. The data is from the beer wings, and the label on the x-axis is going to be hot wings eaten, and on the y-axis is going to be beer consumed. And so let me run that command. All right, there we go. And I don't know if you can see that, but it is labeled wings eaten, beer consumed. I'm going to plot of all the data. And now, if I do the next command, I don't know if anything different happens or if this is just another way of seeing the same thing. The command is slightly different. It's the beer wings, the file, $, focus on hot wing column, the file, $, which means focus on the beer column. So it's going to plot those two variables and then the same labels. I think this is going to show us the exact same plot. Good. Now I can see it's a duplicate because if I go back here to the lower right, this back arrow, forward arrow, scrolls you through the plots you've already done. They look to be the same. Okay. And then this last one, I think we throw gender in there and R defaults to coloring things different colors. Okay. So in the plot, you should now see some things are red. Some of the circles are red versus black. I'm going to guess, since the red tend to be in the upper right corner where more wings and more beer is more wings eaten, more beer drank, those are probably the men who's red. Okay. Okay. So now you know how to do some scatter plots. All right. So last topic in chapter 2 is something we won't use too much, but it's good to have a sense that this can be done. So this is another way of sort of figuring out the shape of a distribution. So I copy this panel down, pause it and copy it down. All right, so here's section 2.7. I've got a random variable, and let's just say I happen to know its mean and its standard deviation. So I'm going to talk about skewness and kurtosis. So the skewness of a distribution is a measure of how asymmetric it is. Does it look to be shifted left or shifted right? Well, not shifted, skewed left or skewed right. Okay, so that's what kurtosis is going to tell us. Kurtosis is denoted gamma sub 1, and by definition, it's the expected value of x minus mu over sigma quantity cubed. Okay, now doing a little algebra and a little expected value math, the cube can apply to the x minus mu and the sigma. Sigma cubed is just a number. It's got no variable in it. X is the random variable, so I can drag it out in front. And I get the expected value of x minus mu cubed times 1 over sigma cubed. This expected value is denoted mu sub 3, the third central moment. Not important to know that, but it's the third central moment over the cube of the standard deviation. Okay. All right, so how do you interpret kurtosis? We can probably calculate it for various distributions, but so what? Well, if your kurtosis is less than -1 or greater than +1, it means the distribution is highly skewed left or highly skewed right. Okay. And look in the book, there's some pictures of kurtosis values compared to the PDF or the MGF of the distribution. Oh, sorry, that was all skewness. Did I say kurtosis? No, getting all mixed up. All right. Kurtosis, the second way to measure shape. Kurtosis is a measure of how peaked the distribution is, or equivalently, how tailed it is. So does most of the probability occur right next to the peak? Or does it have nice big fat tails or one fat tail that contains a lot of the probability as well? Okay, so that's kurtosis, and it's denoted gamma 2. It's defined as that x minus mu over sigma's expected value, the fourth x minus mu over sigma to the fourth power of expected value, -3. Okay. Now some books don't have -3, but then this interpretation down here has to change. But so it's -3, or in other words, doing the same sort of arithmetic we did up above. It's the fourth central moment divided by the fourth power of the standard deviation, -3. Okay. All right. Interpretation. If your kurtosis is greater than 0, then that means your distribution has more of a peak than a normal distribution. And if your kurtosis is less than 0, it has a less of a peak and more tail than a normal distribution. Okay. So in our homework, we might calculate a skewness and a kurtosis a couple of times, but it's not going to be a major focus for this course.